So we are asked, for this problem, 3 to the negative n, is it convergent or divergent? Is it monotonic? And is it bounded for the sequence? So how do we go about solving this? Well, it's quite simple. First, for a convergence, I actually want to rewrite this sequence to look a little nicer. This is actually like 1 over 3 to the n. That's how you could write that. Infinity to n equals 0. And you get the same thing. Like I'll even prove it. I'll plug in 1. So 3 to the negative 1, no, not to the negative 11, is 1/3. 1/3 here. So hopefully that makes sense, that's equivalent. What I want to do now is test convergence or divergence. So I'm going to actually approximate the limit as n approaches infinity. So 3 to the infinity is going to be infinity. So 1 over infinity, that's just going to be 0. So yes, we converge to infinity. Is the function always, and we're going to look at the monoticity of this function, is the function always decreasing? Well, let's do a little comparison. So 1 over 3n. If this is always a decreasing function, right? Because if we make that denominator 2 or 3 or 4 or 5 or 6 or 7 or 8, it's going to keep getting smaller, right? So we are going to make the argument that 1 over 3n is greater than or equal to 1 over 3n plus 1. We also want to say that, we can also say that 1 over 3n minus 1 is greater than or equal to 1 over 3n. Now, I don't care about this because I want to use a little bit of a relationship. I'm going to multiply this over. 1 is greater than or equal to 3n plus 1. Now, I'm going to explain this in two ways. I'm going to use it explaining this, and I'm going to use it explaining this. And hopefully, one of the ways will click with you. So if I plug in 1 for n here, will this always be greater? Well, if I plugged in 1, this is going to be 1 over 3. If I plug in this here, it's going to be 1 over 3 squared, because n plus 1, if I plug in 1, that's going to be 3 to the second. This will be 1 over 9. This inequality is true. And it's going to be true for all values, because you're always going to be adding something to this side. So if that didn't make sense, that this inequality is true, let's define it like this. The ratio between 3n to 3n plus 1 should always be greater than, or sorry, 1 should always be greater than or equal to the ratio here. So this number must always be less than 1. Let's plug in 1 and see what we get. So 3 over 3 squared, that's going to be 3 over 9, which is 1/3. Okay? If I plug in 2, well, let's see what happens when we get 2. 9 over 3 to the 3rd, 27. 9 divided by 27, that's 1/3. So you're always going to find that whatever I plug in for our function here, I'm always going to get back 1/3. This inequality is true. So now that we know this relationship is true, we know that the function or the sequence is always going to be decreasing, right? No matter what I plug in. If my n term was 9, I'd plug in 10 here and I'd still get a lesser value. That tells us that this sequence is monotonic and it's always decreasing. So, are we monotonic? Yes, we're always decreasing. We're convergent to infinity. What about the bounds? What are the bounds of this function? Well, our upper bound, our limit, if we're always decreasing, is going to be whatever value comes first, right? Because if we're always decreasing, we want to be at the first little point. So how we do that is 1 over, and if we're starting our sequence at 0, we just plug in 0. So 1 over 3 to the 0, that's going to be equal to 1 over 1. That's going to be equal to 1. So we are bounded above, or otherwise we have a ceiling. There's a ceiling above us. We're bounded above at 1. Are we bounded below? Is there a ceiling? Or is there a floor? Yes, there is. When we plugged in infinity our last term, or when we took the limit of infinity, we found it converges to 0. So we are bounded below at 0. So we're going to find all of our values in the sequence between 1 and 0. We converge to 0, and we're always decreasing. Hope this video helped you. If it did, please drop a like, comment, and subscribe. I hope that you have a wonderful day.